So hey guys, welcome back to my channel. Hope you're doing extremely well, and this is your very own mask coder this side. So today's question is search in rotated sorted array. So it is just an extension of the previous problem we solved yesterday, which was to find the minimum in a search rotated array, right? Now, let me again clarify what is the meaning of rotated sorted array, right? Think of a sorted array. Think of a sorted array, right? That is, suppose there is an array 1, 2, 3, 5, 6, 7, 8, 9, 10. This array is sorted because all the numbers are increasing, right? All the numbers are increasing left to right, right, as you can see. Now, if I pick a point, suppose I pick this point, and I say rotate the array. That is, take all these elements and push them in front, and take all these elements and push them in last. Like I just want to say that these three elements will be pushed to the last. That is, the array would look something like 5, 6, 7, 8, 9, 10, and the remaining element, that is 1, 2, 3, are pushed to the last. That is 1, 2, 3. Right now, this array and the below array are same. This is an example of rotated sorted array, that is, pick a point and push the elements before it to the last, right? And the order will be preserved. 1, 2, 3 are preserved, right? So this is an example of rotated sorted array. So in this particular array, you have been asked whether a number exists or not. For this particular case, if it is asked that if 3 exists or not. As you can see, 3 is existing, so we have to return its index, which is 0, 1, 2, 3, 4, 5, 6, 7, 8. So our answer for this particular question should be 8. Now, coming on how to solve it. So the brute force is actually very simple. What we will do, we will just do a linear traversal and find if there exists a 3. And as soon as we find it, we return it. As soon as we find it, we return it. Otherwise, we return minus 1. Otherwise, we return minus 1. So, what is the brute force time complexity? So it is running in O of n time complexity and O of 1 space complexity. So it is actually very optimized on its own. But can we optimize it more? Yes, that is why we are here. So whenever there is a question of searching and I'm able to see sorted, search and sort. If these two conditions are there, my direct conclusion should be that can I apply binary search in any case? Can I apply binary search? Because I know that binary search uses the time complexity of O of log n. Right? So this will be an optimal approach rather than O of n, right? Okay, so we are going to think something about binary search, right? But you will say that it is not only sorted, it is rotated sorted. There is an extension. Can we shift our algorithm such that instead of sorted, it works on rotated sorted? What I'm saying is, can we shift such that instead of sorted, it works on rotated sorted? Let me guess. I'm here to deal with that only, right? Okay. Again, let us plot the graph for this particular array. See, suppose this is my array, sample array. Let us plot the graph for it. As you can see, first of all, let us plot a graph for a sorted array. I will try to draw the attention from there. If the array is sorted, suppose the array is 1, 2, 3, 4. How will the graph look? 1 will come here, 2 will come here, 3 will come here, 4 will come here. Right? As you can see, the array will be increasing. Only one direction. You can see it is monotonically increasing. It is monotonically increasing. First point, second point, third point, fourth point. Right? Now, what do we do in binary search is we pick a low. Our low comes here, our high comes here. We calculate the mid. In this particular case, it is 0, 1, 2, 3. So 3 plus 0 by 2 will give me 1.5, which is actually equals to 1. My mid will come here. What do we do in binary search? We say that if this mid element is the element we are looking for, suppose I am looking for key, right? We say three conditions. Mid element is equals to key, it is greater than key, it is less than key. These are the only three conditions. For the first condition, we say we can return our answer because we just found the key. For the second condition, what do we say? Mid is obviously greater than key. We are saying that mid element is greater than key. That the array element present on this particular index is greater than key. That is, key is lying somewhere here. Key is lying somewhere here. What I'm trying to say is, because the mid element is greater than key, that is, key is lying below it. And because it is lying below it, I can say that I can discard the remaining portion. I can discard the remaining portion. That is, I can say my high shifts to mid minus 1. My high equals to mid minus 1. This is what we do. And similarly, when my key is actually greater, that means my key lies here. That means I can shift my low. So low becomes mid plus 1. This is the workflow we use in binary search. Now, what is happening in rotated binary search? So 5 is somewhat here. 6 is 5 is somewhat here. 6 here. 7 here. 8 here. 9 here. 10 here. Right? Up till now, it is correct. Up till now, it is sorted. As you can see, it is sorted up till now. There is no problem. If I can apply a binary search here, no problem. But what happens is 1, 2, 3. That is, these 3 points come here. 1, 2, 3. These 3 points are creating problem. So actually, these are two sorted arrays. Two sorted arrays. So if there is a point that where it has been rotated, if it is given to me, then it is just two sorted arrays. But this point is also not given to me. This point is also a mystery to me. So what will I do? See, I can ideally find this point and then go for these two search separately. But why do I need to expand my work when it is only possible by one binary search? Okay, so how do I do that? How do I do that? Okay, obviously because I'm searching in the all the subarray, my low will be at the starting point, my high will be at the ending point. That is why I will keep my low here, I will keep my high here, right? I will keep my low at this point, I will keep my high at this point. For this particular, let me mark the indexes 0, 1, 2, 3, 4, 5, 6, 7, 8. What is my mid will be? It will be 0 plus 8 by 2, which is equals to 4, right? My mid actually comes on fourth position, which is equals to the value 9. My mid lies here. I'm looking for a value 3. I get 9, right? Now, is there any certainty about this part? This highlighted part, it is not certain, right? It is a zigzag portion. I'm not certain about it. See, when I was doing binary search, I was certain about the remaining part that this is sorted, so this is never going to be in the range. But for this part, when my mid is lying at 9, this part is uncertain because this is zigzag, so I cannot be sure about it. But there is a twist here. I am sure about this part. I am sure about this part. So how can I find this part? How can I find this part? Because mid could have lied here. Mid could have lied here. If this was my mid, then this is a sorted part, and this is a zigzag part. So how can I find mid? How can I find which is a sorted part? So I can just compare my low with mid. I can just compare my low with mid. If my low element is less than my mid element, then this portion is sorted. Then this portion is sorted. As you can see, this particular element is obviously greater than this because it has been mentioned in the question that all the elements are distinct. So only way for a rotated sorted array to exist is this particular element is greater than this, right? This particular element is greater than this, right? Now, what will I do? I will just check if this is sorted. If this is sorted. So again, in binary search, what have we done? We have done low equals to 0, high equals to n minus 1. We have found the mid. Now condition arises if ARR mid equals to key. We don't have to do anything. Simply return. This is same from binary search. Second condition. If this is not the case, then we have two cases. What is the case? If ARR low is actually less than equals to ARR mid, that is, the portion of low to mid is sorted and the remaining portion is zigzag. If ARR low is less than equals to ARR mid, now what? Now what? Now, let us see. We are standing at 9, right? Low to mid is sorted, 5 to 9 is sorted. We were looking for 3. Is there any possibility to find 3 in 5 to 9? No, 3 is actually less than 5. So we need to find something here. Is something lying here? No. We know this portion is sorted. So where can 3 potentially be? Like, I don't know whether 3 is present or not, but if it is there, then where it can be? It cannot be from this to this. So what is the only operation I can do? I can say let us try to shift low equals to mid plus 1. That is, let me shift my low here and then I will check in this portion. Then I will check in this zigzag portion. What I'm trying to say is I am sure that this doesn't lie here. This doesn't lie here. So it might lie here. And for that, I will say low equals to mid plus 1. As simple as that. So what will I do? if array low is less than array mid, that is low to mid is sorted. Let me write it here. Low to mid is sorted. So if my key is greater than equals to array low and key is less than equals to array mid, this is the case when the value which I'm looking for is lying here. If my key is greater than array low and less than array mid, that is this range. That is this range. So what will I do in that case? I will say high equals to mid minus 1. I will explain it. High equals to mid minus 1. Else low equals to mid plus 1. I already explained this. Let me explain you this one. Why I'm doing high equals to mid minus 1. I'm just saying that if my key lies here, suppose my key was 6, I'm standing at 9, I'm saying this portion is sorted, that is 6 is lying between 5 to 9, then I can just say that hey, 6 is lying here, 6 is lying here, because all the elements are distinct, 6 is lying here. So let me shift my high here so that I am able to explore these 4 points, right? That is simple. Okay, so let us move forward. What have we done? We have moved our low here, that is on index number, let me see, index number 5. So my low is at index number 5, my high is at index number 8. So 5 plus 8 by 2 gives me 13 by 2, which is equals to 6. Sixth index is 1. That is my mid occurs here. My mid occurs here. Now, as you can see, my low is actually exceeding my mid value. That is, this portion is not sorted. This portion is zigzag. This portion is zigzag. So, it is else case. It is else case. This condition is not working. This condition is not working. So what will I do? I will write an else block. Else block is for mid to high is sorted. Mid to high is sorted. So what will happen here? What will happen here? Now my mid is here. Mid element is 1. High element is 3. And I'm looking for key equals to 3. That is, this lies in this range. This lies in this range. That means I will explore this range and I will shift my low equals to mid plus 1. Right? So what can I say? In the else block, just write else if key belongs to ARR mid to ARR high in this particular range. If it lies in this particular range, then low equals to mid plus 1. Else I will have to explore other part, that is equals to high equals to mid minus 1. Right? After all the blocks have worked, after all the while loop have worked, and I am not able to return my mid for any, this particular case has not run for any case, that means the element is not in the array and I can simply return minus 1. As simple as that. So I hope the question was clear to you. And now, because this is binary search, as you can see, we are obviously halving all the things one by one, one by one. So it is time complexity O of log n and space complexity O of 1. I don't think that this requires any more explanation, and you must be eager to know the code for it. So let us move to the coding section. So let us start with the code, guys. So int low equals to 0, high equals to arr dot size minus 1. This is simple binary search. Now, while my low is actually less than equals to high, first you find int mid, which is equals to low plus high by 2. First thing is, if it is matching your key, then you are sorted. You don't need to do anything. Return mid. If now mid is not equals to key, so if ARR mid is ARR low is less than equals to ARR mid, that is low to mid is a sorted path. In that case, if my key is greater than equals to ARR low and my key is less than equals to ARR mid, in that case, that is, it is lying in low to mid, so I will just decrease my high because I have a potential answer in low to mid. Else you can shift your low mid plus 1. In the else block, when my mid to high is sorted, in that case, if ARR mid is uh, is less than equals to key, that is, it is lying between mid to high, and ARR high is great is greater than equals to key, because key is lying between mid to high. In that case, low equals to mid plus 1, because we need to discuss about mid to high. Else high equals to mid minus 1, because we are able to we are expecting an answer from the another block, because we are not able to find mid to high. If all the cases not work in the loop finishes, then return minus 1, that we are not able to find a particular answer. Let us try to compile and run it. Hope it will work fine. Oh, there is some typing error. Oh, it is mid, not MD. Let us try to compile and run it now. Let me zoom it also. Working fine for the sample test case. Hope it will work fine for the submission as well. Done. So thank you for watching. Hope you liked it, and make sure to like and subscribe to the channel. Thank you. Have a nice day.